Okay, we are live on YouTube, and I will also record record to the cloud. Okay, the recording also started, so we are good to start the program. So, welcome to the Silicon Valley chapter of IEEE Computer Society. I am the chapter chair, Vishnu Pendiala. Ours is the largest chapter in the Silicon Valley section of IEEE, with over 4,000 subscribers in our mailing list and a strong following of over 12,400 on Twitter alone. We are uniquely positioned by the virtue of location and available expertise, and thanks to the hybrid and online modes, we are able to get excellent speakers like Professor Krishna Kant today, who will be talking on quantifying configuration health of software systems. The synopsis of the talk is something like this. Misconfigurations have been Achilles' heel in complex software systems and are often responsible for the downtimes and enablers of cyber attacks. With the recent rise of the DevOps paradigm, configuration changes have become even more frequent, sometimes multiple times a day, thereby underscoring the importance of correct configuration. In this talk, the speaker will discuss the notion of configuration health index to provide an assessment of how well the system is configured with respect to various objectives and how it can be quantified based on a combination of domain knowledge and available data. The speaker, Professor Kant, will also discuss the challenges in extracting and quantifying the domain knowledge and the selection of tests for diagnosing configuration problems. Here's a little bit of introduction for Professor Kant. Professor Krishna Kant is a professor in the Computer and Information Science Department at Temple University in Philadelphia, Pennsylvania. Earlier, he was a research professor in the Center for Secure Information Systems at George Mason University. From 2008 to 2013, he served as a program director at the National Science Foundation, where he managed the Computer System Research (CSR) program and was instrumental in development and running of an NSF-wide sustainability initiative called SEES, which stands for Science, Engineering, and Education for Sustainability. Earlier, Professor Kant served at Intel Corporation for 11 years, working on a variety of data center architecture and technology issues. From 1991 to 1997, Professor Kant held the consultant position at Ericsson, formerly it was called Bellcore, and worked on many broadband and narrowband telecommunications technologies. Before 1991, Professor Kant was with the Pennsylvania State University as an associate professor of computer science, with research contributions in performance modeling and distributed systems. He received his Ph.D. in mathematical sciences from the University of Texas at Dallas in 1981. He carries extensive experience in academia, industry, and government, and has published in a wide variety of areas in computer science. He has authored a graduate textbook on performance modeling of computer systems and co-edited several other books. Professor Kant is a fellow of IEEE and an IEEE distinguished visitor. Before I turn the control over to Professor Kant, I just wanted to point out that please feel free to post the questions on chat window, and I will relay them to Professor Kant towards the end of the event. And for those who have missed it this time, the links and video Links to the video and the slides will be posted on our website in about a week, if the slides are available, that is. And we'll also put the video, submit the video to IEEE TV for inclusion on that platform as well. So with that little introduction, thanks, Dr. Kant, for agreeing, accepting our invitation, and over to you.
Okay, thank you, Vishnu, for the introduction. I'm happy to give this talk here. And good morning and good evening, wherever you are, I guess. So let's get started. And I want to talk today about the problem of configuration management, which is a very difficult problem. And I believe that not enough attention in academia, at least, has been paid to it. So as was mentioned by Vishnu in the abstract of the talk, that configuration management issues are very expensive. They cause billions of dollars of lost productivity in Fortune 1000 companies. They are responsible for a lot of the downtimes and performance problems that you typically see. Even worse, what happens is that when there is a problem, to diagnose that problem takes on the average 1 week, and sometimes much longer. And the reason for such a long period of time for root cause identification is because most of the methods are typically ad hoc. It's mostly the administrators and people who are knowledgeable trying to put their heads together and trying to find out what actually went wrong and doing a bunch of tests. Obviously, things have been improving in this space. There's a lot of automation available, but still it is not quite enough, given the enormity of the problem. And this problem has become more complex as you go to more agile systems where you are continuously developing and continuously deploying the software. There will always be new parameters or changes in parameters, and the misconfiguration chances go up significantly. Okay, now, although there are obviously misconfigurations in the hardware, but most of the misconfigurations that are troublesome are typically in software. And you can see a pie chart here. It's a little bit old, but if anything, the percentage of problems due to misconfiguration, which is 31%, has only gone up as software becomes more and more complex. So let me start out with giving a real-life example of a scenario which occurred due to a misconfiguration. And this had to do with the setup of Microsoft Office 365 for a large enterprise. And this large enterprise had multiple locations, both in USA and the European Union. So you see the picture here, and the picture shows a couple of locations. Of course, there were many more locations in US and a couple of locations in EU. And they are using on each side a WAN provider, and then it goes through the ISP on each side and through a firewall. Okay. And of course, there is a separate subnet for the US side and separate set of subnets for the EU side. So what happened was, in this instance, was that it was observed that everything worked perfectly when the load was not heavy. But when the load was heavy, then some customers were not able to reach the Office 365 side. In particular, the people from the EU side were not able to access the service, but the access was okay from USA. Now, diagnosing this problem took 2 days, and it involved multiple teams. As you can imagine, that this was a big operation. And ultimately, what they found was that the problem was with the setup of the network address translation NAT. So as you know, what happens with NAT is that NAT has multiple IP pools, IP address pools, and for each IP address pools, it starts allocating the ports, and when it runs out of the ports, then allocates another IP address and so on. So what happened was that during the peak time, there were no more ports left in the NAT pool. So the NAT went ahead and picked up a new IP address and started allocating sessions from that IP address. Unfortunately, it so happened that the next IP address that it picked was from a subnet that actually belonged to the USA. And this is obviously a misconfiguration. And as a result of this misconfiguration, what happened was that all the responses went back towards USA, which means they passed the firewall 1, which was for USA, and the firewall 1 say, hey, I don't know this, and just dumped them. So that was the problem. Okay, now why do we have misconfigurations? Of course, the number one answer is that humans are very error prone and they make mistakes. But that's not the whole story, actually. So even if you could automate everything or try to automate everything, there are a lot of issues in terms of trying to make sure that your configurations will be correct. So number one problem is in terms of specifying the configuration itself. So how you specify what language you use, what terms you use, and traditionally, the specification of configuration has been rather ad hoc and which causes misunderstandings and certainly problems when a person who is trained on one system tries to move to another system. Documentation, the state of documentation is rather bad, might be missing, outdated, incorrect, ad hoc. And then another problem that we see repeatedly is that when users design software, they put in a lot more parameters than what are really required. And generally, the idea is that, oh, we want to make this software as flexible as possible, so we're going to put 20 different configuration parameters. But of course, what happens is that there's not a thorough testing of the different values assigned to those configuration parameters. It's not even feasible because the number of combinations that you need to test out becomes enormous. So basically, we don't really understand what these parameters do, how they interact with others, what are the constraints that you should follow, how you should not set them, and what happens when something is actually misconfigured, because there could be an issue that a configuration parameter in its proper range works well if something else that it is not dependent upon is not misconfigured, but when it is misconfigured, it behaves completely differently. So there are all these very strange kind of dependencies. Now, there is another approach that sometimes software designers take, which is that they try to actually go the opposite direction. They try to minimize the number of configuration parameters. And the idea is to try to make things easy for the user. You have only a couple of very high-level parameters, and the user can only tweak those. And typically, these high-level parameters might have only a few values, like true or false. But that doesn't really solve the problem, because what happens is that these high-level parameters, then underneath, they set a whole bunch of parameters. And if the function and the interaction among all of these parameters is not well understood, then once again, there is a problem. Now, diagnosis also has a lot of problems. There are, of course, limited set of tests that are available that you typically use. And if you need some additional tests, then maybe you get stuck. There are also another thing which is typically not really addressed in a lot of the research, is this notion of multiple parties. And in any organization, and certainly across organizations, there are different subdivisions. There might be, for example, your networking team and your database team. And you cannot really go across and do these tests that, for example, go across through these multiple parties and access things. There might be limitations in terms of what kind of tests can be run and what cannot be run. And this causes a lot of difficulties. So incidentally, I will not be talking about the diagnosis, even though we have done work on that. For lack of time today, I'll be focusing more on the other issues in terms of how we can define a notion of the quality of software. Okay, so let's talk about how we specify configurations. Now, traditionally, the configurations were specified in a configuration file using some ad hoc naming, ad hoc syntax, and ad hoc semantics. And that caused a lot of headache to people, especially if you have to deal with products from multiple vendors. So there has been a movement, particularly in the networking community, and there is something called OpenConfig. And the idea of the OpenConfig is to have a vendor-neutral way of specifying configurations in an XML-like language, which is known as Yang. And this OpenConfig is getting a lot of traction in the networking community. It's largely being driven at this point by the networking vendors. And also, of course, there is a IEEE standardization effort also underway. But still, it's not easy to express everything in a standardized language. And what ends up happening is that there are many vendor-specific versions of Yang, which once again comes back to the same old problem, although it's not so bad anymore, because most of the common configuration parameters can still be expressed in a standardized way. It's only the specialized features that you have a problem. Now, OpenConfig is mostly for the networking. If you want to specify the configuration of storage systems, databases, or other non-networking, then once again, we don't have very good alternatives. So obviously, it is possible to extend OpenConfig and Yang to these other environments, but I'm not aware of much traction in terms of that kind of an extension. Okay, so let me tell you a little bit about what OpenConfig can or cannot do. It's not a panacea. It doesn't solve all the problems. It does solve some of the problems. Okay. So for example, on the right-hand side, there is an example. Of course, all of these XML-based languages are extremely verbose, and it might be a little bit difficult. But basically what this code essentially does is it sets up a IP address for an interface. It sets up the subnet mask, sets up the default gateway, and sets up this Boolean whether the interface is enabled or not. So a pretty routine thing. Okay. So what this specifies is, it specifies, for example, the type of the address. They defined a special type called dotted quad. It's like 10.10.10.15 for that kind of address. It gives you a description what this is for. It also gives you an example. So what this does is that if you have configuration expressed this way, then you have a standard naming convention, you have a standard data structure in terms of how you specify the configuration and all the subcomponents of it. So obviously it's very helpful in terms of understanding the configuration, in terms of setting it correctly, because you're giving examples, you're giving description. However, as such, what it does not provide is the semantics. So for example, if you typed 255.55.255.0 for the mask, well, at least as far as this specification is concerned, it will be considered as valid. Maybe you can add additional things there to detect errors like that, but as such, that error will not be detected. So to be able to detect all of those kinds of errors, you will need to provide a fairly detailed semantics of what each field does and what kind of values it can or cannot take. Even harder problem is that of dependencies. So obviously, for example, the default gateway should be on the same subnet as the host IP, but that dependency is not specified here. Once again, it is possible to specify that kind of a dependency, but you will need some additional mechanisms to do that. Okay, so now let's talk about the issue of trying to find a good configuration. And I would like to introduce through something called Cloud Storage Gateway, and we'll talk about this later as well in terms of defining the notion of quality of configuration. But first, let's see if you're given a CSG or a Cloud Storage Gateway, how we can set a good configuration for it. Now, what is a Cloud Storage Gateway? Well, what it is some local storage, which looks like to the local application, just like a local SCSI storage, except that it's going out to the cloud, and the cloud is typically object store and fetching the data so that the local applications are happy. They don't experience too much latency. They don't experience IO timeouts, and they can behave as if they have access to almost unlimited amount of storage. Now, there are many parameters that you need to set correctly in order for this cloud storage gateway to behave well. And this includes, of course, the hardware parameters such as the CPU core, CPU speed, memory size, memory bandwidth, local storage, IO rate, and so on. Software parameters such as how much space locally you should allocate for the data, how much you should allocate for the metadata, how much you should allocate for the log, and so on. And then, of course, the characteristics of the workload. And it's clear that if you don't configure these things correctly, then you will have all sorts of problems. For example, IO errors and timeouts and high latencies and so on. And it turns out that just randomly throwing resources at the problem doesn't really work like that. Okay, so we actually took a commercial CSG product and on the back end, it went to a cloud actually. And we ran a bunch of applications. And here are the applications that we ran. There are 10 different types of applications. And these are all healthcare applications. They're trying to upload files of different sizes and different number of files. And we collected 1,000 data points. So this was a lot of work. And out of those, 990 points were good. So by doing this, we got a fairly detailed look at what happens to the performance as a function of various configuration parameters. Okay, so now once you have the data, then you could try to look at two different types of problems. One is the simpler problem, which is that if you're given the configuration and the workload, what performance are you going to achieve? Okay, that's the easy problem. Now, instead, what we are interested in is the backward problem. The backward problem is that there is certain target that I have for the performance. Maybe I have some target for the cost as well, which is essential because, of course, if the cost is unlimited, then you could just use unlimited number of resources. So you have some cost limitation, you have performance target, and you put into this black box and out comes a good configuration. And the question is, can we really solve this problem well? So since we have the data, then the first thing that obviously comes to mind is that, hey, why don't we use machine learning? Okay, and we did that. We tried a whole bunch of algorithms. It turned out that the decision tree worked the best. And we also found that the forward problem, that is where you're given the workload and the configuration and you're trying to find the performance, works very well. You have an accuracy of about 95% in almost all the cases. And so that's pretty good. Unfortunately, for the problem that we are interested in, which is that given the performance and the cost, determine the configuration, it doesn't work very well. And not only that, if you're trying to go backwards, then you will need multiple models, perhaps one model for each configuration parameter, which makes this rather impractical. So this is not the way, so a direct machine learning doesn't really work very well. Okay. Also, another thing that we noticed is, and this is very important, is that if you just blindly use everything that you got in terms of the configuration parameters and just dump it into a machine learning model, you don't get a very good result. And the reason is that if you include parameters which don't have much influence on whatever you're interested in performance, let's say the throughput. And there might be many parameters which don't have much influence on the performance, and including them actually makes results worse because it only perturbs, it adds more variability. So what is important is that we actually try to find out what parameters are the most relevant ones, and then use those in the machine learning model rather than just throwing everything in. This obviously people who work with this, they have a clue as to what parameters are relevant and what are not relevant. For example, you would expect that the number of cores, the core speed, and the memory bandwidth, and the disk I/O, and the cache size are all very important parameters. And if you run a principal component analysis on the data, you obviously get the same result. So the principal component analysis kind of confirms the intuition that you have from the domain knowledge that these are the most important parameters. Of course, if one uses the principal component analysis blindly, then you might get something which is not necessarily true. Okay. However, the problem is that it's hard to get a lot of data. In fact, we had good set of data by using our own experimental setup, which obviously took several months to put together. Now, if you look at the public data sets, it's very difficult to get decent data sets for configuration management analysis. In fact, there are lots of workload traces, but they don't really say much about the configuration information. So in fact, we did find a bunch of workloads and their configuration parameters, but there's very little information about what these configuration parameters do. So for example, here I'll just quickly flash these different workloads. They have a whole bunch of parameters like the SQLite, but there's very little explanation as to what they do and how to set them and so on. Okay, so how are we going to set a good configuration if the machine learning doesn't work very well? So what we do is we use the forward model, which works very well as an oracle in a stochastic optimization routine. So essentially in this stochastic optimization, we're trying to minimize the cost, and we have some performance target, and we want to look for a configuration that minimizes the cost and satisfies the performance constraint. And this can be done by a whole bunch of algorithms. I will mention genetic algorithm because it can provide multiple solutions. Some of the solutions that you get may not be very meaningful in practice. So it's good to have multiple solutions, but GA is not a very good algorithm, actually. Mostly it's the worst algorithm. There are other algorithms which are much better, in particular simulated annealing, and particularly we modified it further. We also introduced what is known as tunneling, which allows you to skip over certain regions of space. And by doing all that, so I don't want to go into the details, we can get significantly better performance. And what these graphs are showing is the improvement over the baseline that you get by doing all of these tricks and using the domain knowledge. So let me make it clear that it's not just a different stochastic optimization algorithm, it's the use of the domain knowledge that improves the results quite substantially. So this provides you a sort of a practical way in which you can determine what a good configuration is going to be. Okay, let me move on now to the related problem, and which is that can we, instead of talking about the real output, which could be performance or security or some measure of security or some measure of availability and so on, can we come up with some sort of a score or index, let's say in the range 0 to 1, which gives us a good idea about how good a configuration is. So what is the motivation for this? The motivation for this is that if you're going to do a detailed model for, let's say, the performance or the availability or the security, generally it involves lots and lots of details. And it's extremely complex. It will take a lot of time. It will probably not be very robust. And also the result that it's going to provide you is that generally, although sometimes it's not true, is that more resources you put in, better performance you get, for example. And we're not interested in that. We are interested in how well the system is configured as opposed to how rich it is in terms of resources. So what we would like to do is we would like to compute some sort of an indicator of the quality of configuration, largely based upon the configuration file itself or the configuration files if there are multiple. and not really do a very detailed model. And when we do that, then there is another both plus and minus that you get, essentially, that when you talk about, say, something like performance, okay, so the question that you might ask immediately is, what do you mean by performance? Do you mean latency? Do you mean throughput? Do you mean a throughput of, do you mean the IO throughput? Do you mean the CPU throughput? And that sort of immediately points out to a problem that when you're talking about a precise measure, there's a lot of detail associated with it. And depending upon what kind of detail you provide, you could have different answers. And we want to sort of avoid that. We want to get an index which generally says that this system is well configured from a performance perspective. So it's a sort of a vague notion, and it's an intentionally vague notion, although that vagueness does cause some headache in terms of how you choose the parameters. Okay, so how do we estimate this health index? So basically what we are going to do is as follows. We can represent typically a configuration in form of a tree, particularly if the configuration is well represented using some hierarchical way of doing things, such as a XML object kind of a notation. For example, HDFS and Hadoop have that kind of notation. They have the top level object, under that they have sub-objects and sub-sub-objects and so on. So it can be seen like a tree. And what we do is that we try to find out the health index at some level, not necessarily at the leaf, but closer to the leaf. And then we combine the health indices in some simple-minded way, and we come up with the overall health index. And as a simple experiment, what we did was, we said, okay, how about we combine these health indices by simply taking a geometric mean as we go up the hierarchy. So if we do that, then our whole focus is mostly how to assign the health parameter at the bottom level. Now you will realize that one thing that we are missing if we just blindly assign the health indices at the leaf level and go up is that you will miss out on all the dependencies. So to take care of the dependencies, what we do is we find a core set which is most relevant, and they are largely independent. And then we assign the health parameter to those, and then we derive the health parameter for the others based upon the dependencies, or rather the known dependencies. There might be some unknown dependencies. Okay. So we actually did that for a commercial router. So I will not reveal the name of the vendor, but this is a very complex commercial router, actually. And we applied this methodology. And in this case, this was all done manually. We just wanted to say that if we try to do this manually by spending a lot of effort, and in fact, this did involve multiple administrators who understood different areas of routing, for example, people who understood, for example, about the spanning tree, this and other aspects, VLANs and so on. And they sort of got together and we tried to assign the best possible way the health index. Okay. We did do some automation, and the automation essentially was in terms of assigning same value for similar configuration so that we avoid inconsistencies. And by doing that, what we did was then we plotted the health index of the top level object. And there are lots of top level objects in this router because it's very complex. In this three-dimensional diagram, where you have security attributes here, performance attributes here, and the availability attributes. And of course, the ideal point is this corner here, because there the health parameter will be 1 from a security perspective, performance perspective, and availability perspective. But we found, of course, that there is a spread. And what this sort of tells you about which objects are not performing very well in terms of their configuration, and you could look at them and try to improve the configuration. So there is a utility to doing something like this. The issue, of course, is that trying to do all of this manually is very, very expensive. And you can do it once, but you're probably not going to repeat it. Okay, so how do we do the automation? And talk a little bit about what are the challenges in doing the automation, first of all. So first of all, when you look at the data that is available, there is generally 2 types of data that is available. There is typically a lot of performance data that would be available. And then in addition, there will be data available regarding failures, regarding the security intrusions, and all of those other problems. Okay. And we can definitely make use of that data. The problem with this, most of this data is sparse, that it is sparse. Now, you can easily understand that the data about the failures and the security intrusion and operational problems is rather sparse, because hopefully they don't happen too often. But why do I say that the performance data is also sparse? The reason is that you have lots of configuration parameters, but generally, at least in the production cluster, you'll be setting those parameters to values that are quote unquote good. They're working values. So the range of the parameter space or the portion of the parameter space that will be covered by all of the data. You might have tons and tons of data, but the parameter space that will be covered by this data is likely to be very much biased towards good configuration and not enough about the bad configuration. Now, why do we need to worry about the bad configuration? Because the whole idea is that every once in a while, when you do have a bad configuration, you are able to diagnose that or detect that, or somehow using this metric, find out that there is something wrong with the configuration. Now, if you take the data from the test cluster, which can generally do a lot more varied experimentation, there you might have some difficulty in terms of generalizing it to the production system. Okay, so the big question is that since our data is sparse, how do we augment the data? Okay, that's a big problem. Now, the first answer that obviously comes in is that, well, we are going to use machine learning techniques to do that. In particular, we are going to just use semi-supervised learning, for example. Okay. Now, what we found out is that if you entirely depend upon the data and try to find the behavior of the configuration variables based upon the data, you often come up with very misleading conclusions. Okay. So for example, if you take, let's say, all of the data and we try to do the piecewise linear fit, which is a very popular thing to do, and there are these 2 different algorithms which can do that. So basically, they take this multidimensional data, they try to fit linear regression, but in steps, so that you could have a line which has a small slope for a while, then it has a larger slope, and so on. Now, what happens is if you do that, then you end up with fairly nonsensical results. And I'll show you that. So in fact, we actually did that. And we did that not only on the CSG, where we have a very complete data. We also did that on these other workloads where we don't really know a whole lot about all the configuration parameters, but at least as systems people, we do know something about these. We know, for example, that things like the number of CPU cores, the CPU capacity, or the cache size, some of these things should matter a lot. But what turns out is that if you run these algorithms, then they ignore some of these very crucial parameters. So for example, in case of CSG, it gives you a fit based entirely on the file size, the number of files, and the number of cores. It says that the core speed is not important. I'm going to ignore it. Memory bandwidth is not important. I'm going to ignore it. The disk I/O bandwidth is not important. The cache space is not important. So you can imagine that how wrong this is. And the same thing applies to the others as well. There's another representation of that using Lars, basically saying that only there are some of, this is for the CSG, this is for BitBrains, that there are only some of these parameters which are important in determining the output. Everything else is irrelevant. And these are totally wrong and misleading results. Okay, so we cannot blindly use data. And also, if you try to just use the data, the available data, and then follow the normal semi-supervised learning techniques, where you basically run it, and then you label some more data with higher confidence, well, that's not going to work either. So here, for example, it turns out that the mean square errors are pretty low, which means that these guys are pretty confident what they're doing is right, except what they're doing is nonsense. Okay, so what we do is that we take the approach of first figure out some key configuration variables. And this comes largely from the domain knowledge, as you could use principal component analysis for it to some extent. And then once you have that, you use the known rules of thumb to estimate others. So for example, if the rule of thumb says that as you increase the number of cores, you also increase the memory, for example, then that will be a rule of thumb and you can use that directly. Okay, so for the key CVs, you start with the domain knowledge, and instead of directly determining the output, you determine some parameters that go into determining the output. And that way you reduce the number of parameters that you need to determine, and you will determine the sensible parameters. And then one could apply the semi-supervised machine learning. Okay. So what are some of the relationships that we use? I already gave you an example. There will be some strong relationships, such as a higher CPU speed means that higher memory bandwidth and lower latency for the memory. Weak relationships that if you have a 4-core machine, then your memory should be in that range. So you could have rules of thumbs. And then another domain knowledge that you typically have is, for example, the idea of a diminishing return. So for example, here, if this is your performance and this is some parameters, let's say the cache size or what have you, generally you will see a behavior like this. In some cases, you will see even a decrease in performance, ultimately, a kind of a unimodal behavior. For example, if you have a number of threads, as the number of threads increases, at first the performance increases at first and then it goes down because of the overhead. So what we do is that instead of determining the performance, we assume a certain form, and then there are only 3 parameters, which is the growth factor, the decay factor, and the mode point. And then we determine those, and then we get the result. So based upon that, we have this entire system running out of time. So let me speed up a little bit. We have this entire mechanism that we came up with in terms of how we can determine the health index and make sure that it is sensible. Okay. So here are some results. I'll show you. So based upon this rather simple analysis and the domain knowledge, we find out, for example, for the CSG, what you would expect, that having too much cache actually hurts. So with cache, at first the performance goes up, but then it comes down. And too much space for the metadata also hurts, because if you allocate too much space to the metadata, then you don't have enough space for the data, and therefore it hurts again. So these are very logical things that you would expect, and we get that by following this kind of a methodology. And we also have some validation, shows that our predictions correspond to the actual measurements. And we applied the same methodology on these other data sets, and we get substantially better results. For example, here, compared to what is known as the best known results, or the state-of-the-art results that are reported in other papers. In fact, there are other papers which report for some of these workloads that these workloads are too bad and we cannot really determine their performance. And the reason is that most of these analyses were based upon the data only and did not use the domain knowledge. And it's the domain knowledge that really gives you much better. Okay. So this is my last slide. So the question is that, can we quantify the configuration quality? The answer is yes, but we need several things to be in place to be able to really do that job. First one, which we already have to some extent, that we need a standard way of specifying the structure and representation of the configuration. Now, OpenConfig does provide that, but that's only good for the network. There is still trouble with the vendor-specific features, so there are issues with OpenConfig. And it is not available for other types of configuration. But there is hope in terms of having a standard way of specifying the configuration. In addition, we need a more detailed semantics and constraints so that we can define the dependencies and the rules of thumb that I was talking about. And similarly for the dependencies within and across the modules. And we need a way of specifying those, because if you don't have those, then we are not able to determine how the configuration of one object should relate to the configuration of another object. It will have difficulty. So if there is a good way of doing that, then we can solve this problem. So given all this, I think if we can define a way, a health index of the type that I talked about, then we can have a handle on characterizing the quality of software configuration. Now, one other thing that, again, I will emphasize is that just blindly using the data to find the facts is very, very dangerous. And what we have found is that it often leads to very misleading results. And in fact, by making use of domain knowledge, now there are problems in terms of specifying the domain knowledge, in terms of curating the domain knowledge, in terms of trying to try to identify discrepancies in domain knowledge. But if we can do that, then we can apply the domain knowledge, we can do a far better job than just blindly using the data. And I think that's all I have. So thank you very much. And I think I am on time. We started at 10 minutes past, I guess. So I'm open for questions now.
Yeah, thank you, Professor Kant. It was really very insightful. I think the issues were very well brought out, and the Microsoft example that you started with was really great. So any questions from anyone on Zoom or on YouTube? Let me check YouTube. We have 2 likes, but no questions on YouTube, and there are no questions on Zoom either, but I have a couple of questions myself, Professor Kant, if it's okay.
Sure.
So it looks like your software is, the proposal that you made is for the work that you described is to determine the configuration parameters, whereas tools like Ansible, Chef, and Puppet actually manage the configuration.
Mm-hmm.
Right? Is there a better relation between the two, or did I miss something?
Okay, so I think there is a little bit of a misunderstanding about these tools. What these tools do best is try to take a configuration and distribute it to a large number of servers in a consistent manner. And that's the job that they primarily do. Now, you can write some code in these to set up the configuration and then copy the configuration, maybe even update the configuration. But most of the semantic information that goes in terms of doing it correctly is done by a human there. So these are 2 different problems. So one problem is, how do we determine the correct configuration parameters, which will satisfy the dependencies, which will give you a decent behavior? And then the other question, which is, by the way, is a very important question in a large organization, is how do we distribute the configuration to thousands of servers, and particularly in an environment where the servers might be of different sizes and different operating systems and so on, and how to do that in a proper way. So both are needed. So these Ansible and all of these other software, they are valuable, but they don't do everything that we're looking for.
Okay, so your work basically automates the human part of it.
Right. Well, at least hopes to.
Yeah, that's right.
We can never automate a human. I hope not.
Yeah. And is this in production already, or somewhere?
So this is research, and this is, let me be honest, this is academic research. So this is not a software. This is something that we did in a software. This is limited. We have done some experiments. We have applied this, but in terms of having any kind of sort of a software that somebody can just use, no, it's not there.
Okay. So just theoretically, in that case, if we extend this to production, any ideas on how we can manage the data drift? Because the data will keep changing, I believe, right? From the logs and all that. If you collect the logs dynamically, there will be a drift.
Sure.
So any ideas on how to manage the drift, data drift?
Yeah, so thank you for bringing that up. I think that's the data drift is a very important part of working with real systems. So everything kind of drifts, right? The policies change, the behavior changes, and the workload changes, and so on. So if you have a way of characterizing the quality of the configuration in an easy manner without going through all the gory details of very detailed modeling or detailed performance characteristics, then it helps in terms of tracking the data drift. So you can automate this process, perhaps. You can continue to collect data and feed it into the system. And it may be that at some point it says that certain objects are not very well configured. And then you can go and look into that and see why they are not configured. And perhaps maybe there is a scope for some additional automation in terms of trying to figure out why they are not well configured and what can we do about it. That's sort of the diagnosis kind of an angle in terms of. But yes, I think this methodology certainly helps in terms of trying to track things down and continue to update your configuration as things change.
So thank you for that answer. I think in the interest of time, I have a few more questions, but in the interest of time, we can probably conclude, and maybe folks can reach out to you if there are any questions offline also, right?
Yeah, absolutely. So I guess my email address is there.
Yes.
Okay.
Yeah. It's there on the internet. So it should be pretty straightforward to get your email address.
So absolutely feel free, and I respond to emails pretty promptly, typically. So, so yes, feel free to ask questions.
Yeah, I can vouch for it. You responded very promptly to my cold email, almost inviting you to the event. So thanks again, Dr. Kant. If it was in person, I could have presented a plaque to you, but in the absence of that, here's a small token of appreciation, a certificate from our chapter for acknowledging your talk today. It was really a great, insightful talk. I'll submit it to IEEE.te for others to watch as well in future, and it will stay on YouTube. So thanks a lot.
Okay.
And I will send you by email as well.
Sure.
And
okay, thanks very much. It was a pleasure to talk about this, and hopefully this will result in some questions, and perhaps people will follow up on this and do some further work.
Yeah. Thanks a lot, Professor Kant. And yeah, I know it's good night for you. It's almost evening for you. So have a great night. And
okay, good night.
Yeah, thanks. Bye.
Okay, bye.
Bye.